thanks to Walter for the opportunity to speak in this seminar series. I'd like to tell you about nonlinear reduced order modeling from data today. And just a very quick motivation slide for nonlinear model reduction. There's two classes of problems in which model reduction is very important. In the first class, we do have a good idea of the governing equations, but they are too complex. There's too many of them. In the second class of problems, we may not even know the governing equations in detail, but we would like to explore them. So we're able to accumulate data, but there's too much data. So we would like to have a simpler understanding, a simplified understanding of the dynamical system. So in the first case, we talk about equation-driven model reduction. In the second case, and that's going to be the emphasis today, is data-driven model reduction. More often than not, the resulting equations will be nonlinear, the reduced equations, because the process that we would like to model is intrinsically nonlinear. Hallmarks of that are coexisting multiple attracting steady states, bifurcations, and transitions among them, which cannot be captured by linear models. So I'd like to do that in a mathematically justified setting, at least for the problems that I'm going to discuss today. And one such mathematically justified setting is when we know that there exists a lower dimensional attracting invariant manifold in the phase space, which is the space of positions and velocities. So if it's low dimensional attracting and invariant, then it makes sense to explore its intrinsic internal dynamics, because everything else will be attracted to the manifold and will synchronize with the manifold. However, that picture is only correct, in fact, if the manifold is not only attracting, but also normally hyperbolic, which means that the attraction rates are stronger, normal or transverse to the manifold, than any potential attraction rates or a contraction along the manifold. In that case, we call the manifold normally hyperbolic, or just informally a slow manifold. It's important that the manifold is slow. I'm showing you here invariant manifold, which is attracting, but it's not a slow manifold. It's not normally hyperbolic, because the decay rates transferred to the manifold are in fact faster than the decay rates along the manifold. And you see what the issue is, that most of the time you're not synchronizing with what's happening on the manifold. You're just flying parallel to the manifold. Only in the end do you actually converge to the attractor within the manifold. So this is not a good setting for model reduction. The good setting is when you have normal hyperbolicity, meaning that the transverse attraction rates actually dominate the tangential ones, and that means you're approaching this manifold as you would approach a slow manifold. So such a manifold is often called a slow manifold in fluid dynamics, inertial manifold, and it contains the final attractor. So this is a very appealing mathematical picture, but important to know whether this manifold exists. Is it smooth? Because we would like to do calculus on it. Is it unique? And most importantly, how do we find it? And there's no general answer to these questions. No general answer, but in the setting of nonlinear vibration and structural dynamics, we're much better off than the general setting, because we can in fact start from the linear limit of the system, and in linear systems explore that and extend our knowledge to nonlinear systems. So in the linear systems, these slow manifolds are in fact slow spectral submanifolds that we can fairly explicitly construct. What are spectral submanifolds in SSMs? They are invariant manifolds that are tangent to slow eigenspaces, to eigenspaces spanned by modes that are more slowly decaying than others. And this is very explicit in linear systems. I just give you the simplest example of a planar differential equation, a two-dimensional node. The y direction decays faster than the x direction, so beta is larger than alpha. You can think of this as a toy model for two overdamped modes for the amplitudes of these modes. And then this is the phase portrait. So in the x direction, the x is a spectral subspace. It's a fancy term for just this invariant line, but in this example, it's just a line. In higher dimensional examples, it is indeed a subspace. And it's a slow spectral subspace, which is also, it coincides with a spectral submanifold because it satisfies this definition. Itself is tangent to itself and the origin. So it's a slow spectral subspace, also slow spectral submanifold. It's flat, so it's C infinity. There are many other such manifolds that are actually tangent to the slow subspace at the origin. But if you work out their form, their functional form, which is easy calculation, it's x to the beta over alpha type dependence. So it's only finitely many times differentiable depending on the integer part of beta over alpha. So there's a dramatic drop of differentiability down from infinity to finite. So long story short, when you have spectral subspaces, slow spectral subspace in linear systems, then there will be already in the linear limit a smoothest spectral submanifold, which is the subspace itself, but there will be many other invariant manifolds of the same dimension that are also tangent to that subspace. They're also invariant, but their differentiability is much, much less in general than the differentiability of the primary one. We call this secondary or fractional one. So this turns out to generalize this picture to arbitrary nonlinear systems first. I'm not going to do all the cases, but more importantly, if you add nonlinear terms, then it turns out that under just fairly weak non-resonance conditions, the picture that you understand for the linear system carries over to the nonlinear system. So there's a result that has been known for quite a while now, originally in the more pure math literature, which we translated in 2016, and basically says that the equilibrium point, fixed point, is asymptotically stable, and there's no slow fast resonance, so no linear combination, non-negative linear combination of the slow eigenvalues hit a fast eigenvalue with these coefficients. Then the linear picture carries over to the nonlinear system when you add the nonlinearity. So basically, a unique primary SSM smoothly persists, the primary one that has been well known. So in this picture, this theorem would guarantee that if you take the green entity, that it will deform, but it will continue to exist when you add the nonlinear terms, and it's equally smooth. Okay. This was in fact a math result from 2003, but it was actually fully anticipated in the nonlinear vibrations community. There's this seminal paper by Steve Shaw, Christophe Pierre, in which they foresaw that the existence of this manifold, they assumed that it exists, and they were happily doing calculations without necessarily worrying about the details of the mathematics. It's a very influential paper that motivated many of us to work in this area and basically gave a rigorous foundation to model reduction and structural dynamics. But the question is, what happens to these others? And those turned out to be actually equally important in a data-driven setting later on. So more recently, we looked at this problem and extended the result, the mathematical result. So you can also allow for instabilities. So we only require the real parts to be non-zero, but there can be some eigenvalues within the slow manifold and the slow subspace that are unstable. And as long as there's no full resonance among any of the eigenvalues except for the 1-1 resonance, then also the fractional or secondary submanifolds of the linear system can be extended. So the fractional SSMs also smoothly persist. So if this was the linear picture, then when you add the nonlinear terms, you can just imagine a smooth deformation of this, which is probably not surprising at all. However, we now have explicit functional forms for these. We know exactly how smooth they are, and we know what functional form we should be looking for them. Equally important is what happens when you add forcing to the system. And the original result that was known in the literature, again, first in the more on the pure side of dynamical systems literature, which we also translated in 2016. Basically, if the equilibrium point was stable and you're adding small time periodic or time quasi-periodic forcing, then as long as there's no resonance among the real parts of the slow and fast eigenvalues, then under small enough periodic or quasi-periodic forcing, what you see in the original linear system carries over not only to the nonlinear system, but also to the force system. So if you look at this original Shaw-Pierre example and you start forcing it, then what transpires is essentially you will have a periodic orbit into which the equilibrium point perturbs, and you have this magic carpet that moves periodically, and you can reduce your system to that and get a reduced order model. Important open question has been, what happens when this forcing is more general? And only recently, that took us a while to figure out. But the good news is that we have results for that case as well. Again, we can also allow instabilities within the slow subspace. And we again have to exclude real part resonances among all the eigenvalues, all these non-resonance conditions are satisfied by still, they're not violated by 1-1 resonances, which are quite frequent in symmetric engineering systems. So those are okay. It's just the other higher resonances that are not okay. Long story short, when you have non-resonance, then a unique primary smooth SSM also exists after you add the nonlinear terms and the forcing, as long as the forcing is small or slow, which is often the case in practice when you apply forcing to structural dynamics problem. So here's an example in which Roshan, who was a co-author on this recent paper still under review, consider this example basically a Charpier oscillator on a cart, and applied chaotic forcing to this. It started shaking it with a signal from the Lorentz attractor, so it's as chaotic as it gets. And this new theory actually tells you the exact shape of what arises as a generalized steady state, a chaotic steady state, the generalization of a periodic steady state or a quasi-periodic steady state. We now have formulas for a general aperiodic steady state, including chaotic one. And an attached spectral submanifold, which will, again, be a sort of a magic carpet, but it will now move with that general time dependence that can be chaotic. What you see here is a simulation of the system. The full model is black. The SSM reduced model is red, and these two catch up with each other, and together very quickly, and together they chase the generalized steady state, which is chaotic. And they do so along this chaotically moving spectral submanifold, for which we now have explicit formulas. So that's been quite an exciting development. And we are in the process of extending this to higher dimensional problems, say finite element problems. Big question, how do you do all this when the equations are not available, only data? So that brings us to this now open source, publicly available software package, SSM Learn, which you can download from here, developed by my group. And basically, I don't have time to go into the details, but you can use this package to construct spectral submanifolds from data. So in some space of observables that range from Y1 up to, say, YP, the code identifies a dominant slow spectral subspace and then looks for a spectral submanifold tangent to it. In lots of problems, it's very low dimensional, essentially two-dimensional. So it returns a two-dimensional reduced order model, even if you had millions of degrees initially. So no time to go into detail, but I recommend this paper, which has all the details. You essentially start from data that you get from your observations, observable data. This is a data matrix. And the idea is to regress after you have cleared up the basic geometry of the slow spectral subspace to regress an SSM, a spectral submanifold to that, which is a graph to it, and also regress its reduced dynamics to the available observational data. Once you have the reduced dynamics from this, then we apply generally a normal form transformation, which simplifies the reduced dynamics. It's an extended normal form transformation, which means we don't transform out everything we could, because we also keep the terms that are near resonant. That enables us to deal with nonlinearities. We don't seek to linearize on this manifold. And finally, we can add forcing for prediction, the leading order forcing. We can predict, you learn this part, the black part of the reduced equation, and you can symbolically add forcing to that, because we know how to add it, basically project it up to linear order to the spectral subspace and make predictions about the system that you have not seen, the force system. And this was the first example in which we did that. This is fluid sloshing by the Avila lab, Kerstin Avila, who recently got a professorship at the University of Oldenburg. There's these fantastic experiments, fluid sloshing in this container, which is being shaken. And the observable here is the center of mass of the fluid, which one can calculate from the available videos. And just for reference, if you did linear model reduction of this, you use the dynamic mode decomposition, you could fit a very good DMD model to this decaying data without forcing. So that might give the idea that most likely the system is linear. But if it's really linear, then we should be able to make predictions for the force response by adding the appropriate forcing term, which we understand well. in the observable space and make predictions for the force response. So this would be then so you learn this part of the model, and then you add the forcing here after necessary calibration and try to make a prediction about the force response. And you see here that the predictions from this DMD-based model, which are the solid curves for various forcing amplitudes, are very different from what actually transpires in the experiments. DMD is a fantastic method, and it actually works quite well for low amplitudes in the linear regime. But when you have nonlinear response, which means that for a given frequency you have coexisting stable and unstable periodic orbits, a linear system cannot capture that. So clearly we need a nonlinear model. So if you do this with SSM learn, again, just two trajectories, you perform the procedure that I described. Here's the experimental data, and SSM learner also fits that trajectory to that. But this is a nonlinear model. It does look like, linear decaying response, but it's now a nonlinear model that's been inferred on a two-dimensional spectral submanifold using 5-dimensional delay embedding. I don't want to go into the background of this. This paper has all the details as to why you pick these dimensions. And this is the actual equation, normal form in polar coordinates on two-dimensional spectral submanifold. Rho is basically an amplitude, and psi is the difference between the forcing phase and the polar angle that you would normally have in this normal form. It gives you an autonomous system of this general form, and this is constructed based on unforced data, and we are in the position now to make predictions when we add forcing. Just symbolically calculate the fixed points of this equation. In explicit form, we get them. And by hand, you can do this. This is the solution. You can make predictions for the force response, and then you ask your experimentalist colleagues to do the experiments and see whether they match or not. And the match is amazingly, the fit between the two is amazingly close. So what you see here is the force response. These are the red dots of the experimental points, and these are analytic predictions by hand from these formulas. And we can also predict whether the response is stable or unstable. An experiment can only predict stable response, right? But the two are incredibly close. So it really tells you that it's worth investing in understanding the dynamics in detail. Again, understand that the model is trained on unforced data, and then you change the dynamical system to a forced dynamical system, and you can make such accurate predictions, not just for the response amplitude, but also for the response phase. It's very accurate. So that was very encouraging. That's why we wrote that initial paper. I would also show you a more recent example. This was an experiment in my colleague's lab, Jörg Dual at ETH, who does really high-end gravity measurements using beams. And you see this oscillating beam here. The input to SSM learn was velocity measurements from this laser. And this is the best we were able to do in terms of a backbone curve, which is basically the instantaneous amplitude as a function of the instantaneous frequency on decaying signals. It's not how a classic backbone curve should really look like. Now, the textbook example of that, it's slanted, and it's also wavy. So it gave us a headache for quite a while. We gave this, the data decaying data to SSM learn, just one scalar unforced velocity signal. The output was a 7th order normal form on a two-dimensional SSM, but we were not fitting. In fact, we could not fit to this type of a backbone curve and the force response curve. So we wanted those as model outputs and predictions. And when you do that and you assume that fundamentally the data is near the primary spectral submanifold, then you see the prediction by the reduced order model for the backbone curve, which is in green here, and for the force response is quite off from what you actually measure experimentally. Why? Because this was all based on the assumption that those fractional submanifolds don't matter. It's really the primary ones that we can use in reduced order modeling. So after lots of scratching of heads, we went back and looked at, well, what if we actually throw in the fractional spectral submanifolds? And the minute you account for that, immediately much better fit. But then we came bold and said, you know what, this is still not perfect. It's very good. Is it possible that we are right and maybe the experimental data is not quite accurate? It turns out, yes, that was the case. So they were doing the experiments at different times. and they were not watching out exactly to keep for the temperatures, that there were significant temperature variations. And when you actually repeat the experiments, which they did, and make sure that the temperature remains constant, then you actually get a perfect fit. So this was the type of output that I would like to see us give from our reduced order models. So we don't just fit to existing phenomena, but we're able to tell people things they didn't know, or even we're able to uncover errors in the experiments because our analysis is correct and shows an inconsistency within the data set. This is one of the other example I wanted to show you. This is basically a data-assisted finite element simulation. That's what we call it. So it's a very high degree of freedom MEMS gyroscope, more than 1 million degrees of freedom. It's a pain to simulate. So in COMSOL, this one decaying trajectory took a lot of background work back in probably months. And after that, 2 full days of simulation just to get this, right? And for all we know, this could be in the linear regime, but it turns out it's already in the nonlinear regime. Well, what we did, we used this as input to SSM learn, this one trajectory, and from SSM learn identified a reduced order model, nonlinear one, on a 2-dimensional spectral submanifold, on which we were able to then make explicit predictions for the force response by hand. This is the actual normal form on the 2-dimensional spectral submanifold learned from the data. Is the same calculation I showed you before for the sloshing problem. And this is the force response calculation by hand, which, just to give you an idea, once we have this data, then SSM learn, it takes 6 minutes for SSM learn to predict this whole curve. And it now can predict for any amplitude within seconds. That's just a one-time 6-minute investment. To verify it means you have to run the force response. And just to run one of these force response points, just we are only able to do 6. It takes us anywhere between 40 or 50 hours, but only if you actually use the results from SSM learn. So you start the initial conditions near the SSM learn prediction. If not, so this already uses the prediction for SSM learn. If not, then it basically, I don't think it would ever converge. Certainly not within a reasonable amount of time. At some point, it would converge, but of course, you run out of memory, you run out of machine time, your job gets terminated, all these problems. I wanted to show you finally an application to controls. We're working with Marco Pavone's lab at Stanford, who do great work in constructing model predictive controls for soft robots like this. And soft robots are very high degree of freedom continuum robots. You can't just model them by, say, 2 or 3 rigid bodies and springs and dashboards. The model would be a finite element code. So here you really need to reduce, for controls purposes, the code. Here there was an additional step. Not only did we learn the reduced dynamics, but also had to learn the controller. That's a different story, how the control appears in the observable space. But using that one, they compared different controller strategies. Ours is the SSM-based one, is the blue one. And the target would be just this dashed line. And you can see that we get the closest to that in the iMetric. They also used other techniques that they had implemented in the lab. One of them was trajectory piecewise linearization. The other one is Koopman or extended DMD. And in the iMetric, we're doing the best. But I think what really is interesting to look at is the actual model dimensions versus performance. The SSM was a 6-dimensional model, 2 dimensions for each degrees of freedom, and the mean squared error was 5.06. The trajectory piecewise linearization was a 42-dimensional model, so that's 7 times as large, and the error was 6 times as large. And finally, EDMD or Koopman was 66-dimensional. The dimension was 10 times as much as our model, and the error was then about, what is it? It's 20 times as much or even more. So it does pay off to invest in learning the dynamics. So finally, I just wanted to show you the ongoing activities in my group. We're exploring further the use of fractional SSMs and in various experiments. They turn out to be very important. We continue to work on model predictive control of soft robots, other very active area where we think that SSM-based control is very important. And finally, very exciting work of modeling and control of hydraulic actuators with memory, where it turns out that SSMs can also be used in that setting to model systems with memory. So I'll stop here and thank you for your attention.